Hey everyone, welcome to another live coding. Hope everyone had a great week. So in this live coding I'll be detecting brain tumors in images, and we'll be doing it with a normal classification model and using a little bit of pre-trained models in there as well, specifically VGG. Start with a funny story. I really wanted to run on Cloud for this one, but Cloud did not want to run with me. So we'll be doing everything locally, and hopefully it runs well. If it doesn't, things might crash, and in that case we'll probably do a retake next week. But let's cross our fingers that everything works as it should, and let's jump into it. So, first thing first, let's have a quick look at the dataset. So here's the dataset I prepared, and we have here two different folders, one with no and one with yes, where no is no brain tumor and yes is with something. So taking a look at these ones, we can pretty visibly see just from the images, without any machine learning, where the brain tumors is. So hopefully this wouldn't be too difficult for our model to start learning as well. Then besides that, I also prepared this CSV file. Let's see if I can show it. There we go. Just like last time, or very similar, we have a bunch of images labeled, bunch of images over here, and these are all the images in all the folders, and then we have the labels over here as well. So that's everything we need to prepare to get the data into PerceptiLabs. So let's create a model around it and see how it works. Alright. We're also getting data partition in here. This one will soon get a visual interface update, so it'll look a little bit more like a designer designed it and a little bit less like a front-ender designed it. But let's fill in the input-output as well as the different data types. We want these ones to be images, we want these ones to be categorical, and it will automatically translate the yes and no's into two different categories. And then we'll just create the model. Alright, so here we have our model, and we can delete everything to start with. So we're going to use a VGG16 pre-trained model, as I mentioned before. And VGG is a model which consists of traditionally 5 groups of convolutional layers. Each group has a pooling in between them. And then finally it has 3 dense layers at the end of it as the output. Since we're using a pre-trained layer and we're removing the top part of the model, we don't include the top over here. Those 3 dense layers are not going to be included, and the output we're going to see will instead be something like this. So we're getting the output of the last pooling layer in this VGG model. The reason I'm using VGG, it's really high performant considering how relatively small it is, and it's pretty cool because it is just convolutional layers compared to some of these more complex models. So after we have our pre-trained model, this one, just like before, will not be trainable. So we're not going to train it, we're just going to use it to extract features from the images. And the trainable part of our model will instead be these 2 dense layers. So we'll have one dense layer here, which will be kind of a midpoint for the model, so we don't go straight to the output. And we'll put it to 128 neurons. I've seen a bunch of variety on what this one can be: 128, 256, 512. 128 has been working really well for me, so we'll go with that. Then we have the output. The output should have a softmax in it. The reason we have a softmax is because we're doing categorical training, so we want to make sure that these ones always stay between 0 and 1, which is exactly what softmax do. Softmax just make sure that if you sum up all of these categories, they'll become 1. And that's the model. So let's try running it and see how it goes. I'll be using a batch size of 32. It's not the hugest dataset or the largest dataset which we're using, so even batch size of 32 might be a little bit large, but we'll try it out and see how it goes. And then we'll start running. I also changed the loss function to cross entropy, which is very standard for categorical. I just realized we probably shouldn't have run it for 100 epochs, but that's fine. We'll just stop it as soon as we see that it's good enough. All right. So let's look at the usual things. Let's look at the gradient and see if it exists. And as soon as it's gone a little bit, I'll swap over to accuracy to see that as well. The accuracy for a completely untrained model should be 50%. So anything above that is going to be just improvement. Last time I ran it, Alright, I think I'm back. Maybe? Alright, looks like I'm back. Let's see if anyone managed to find back to the stream. Sorry about that crash. We finally got the cloud up and running though, it seems. Just a little bit too late, but yeah, back and now running on cloud. So this should work a lot better. Alright, while we're waiting for everyone, we'll catch up on where we were before and just load all the data. I did not mean to save the model, but that's fine. Alright, let's delete these layers. That's a little bit too much. Let's delete the middle layers, so we keep the input and output. Then we drag in the VGG again. I think we can hide these tips. We add a dense layer. And one more dense layer. All right, cool. Let's start training again, and hope that this should work a lot better, since it's no longer trying to use my local CPU. So where we last left off, or last crashed rather, we were at about 80% accuracy. Ignore that it says IOU here. This specific version was built for a segmentation task. Hopefully we can show that soon as well. But this means accuracy in this case. So, as we were saying before, since we fairly easily could see the difference between someone having a tumor and not when comparing the images side by side, I wouldn't be surprised if the model also managed to do that pretty well. We can see that the gradients are changing, which means that everything is updating as it should. And we're starting at this time at 35% accuracy instead, but fairly quickly going up, it seems. With the VGG here doing a lot of the feature extraction, and it's been trained on a lot more images with quite a lot of complexity. This probably should learn pretty well to tell these apart. And if it doesn't, we will try something else real quick. You can see at least the samples we're looking at seems to be predicting all right. I'm gonna go quick back here as well to see if these two have the right settings, which they do. And this one looks fine as well. Well, we are getting pretty decent accuracy, 77% or 50 in some cases. It's starting to increase over that 50% mark, which would be if you just took an image and randomly selected it. Since there are two different classes, it would be 50%, essentially as a coin flip. So that's more or less where the model starts off. If you're wondering why the validation accuracy is so low every time at the start, it's because we haven't seen any validation yet for it. But I think we're gonna do either remove it when it hasn't been seen yet, or just placing it on the same line as last time. Sebastian had a question if the software features are paid. This is completely free. You can go and download this through a pip install PerceptiLabs right into your Python environment if you want that, and you'll be able to do this. The version I'm running on right now, though, is a Docker version in AWS, and the Docker version is an enterprise version. But if you're interested, just feel free to reach out to us either through Slack or forum, and we can see if we can set you up. Okay, well, it's getting better and better. I figure we maybe let it go to 80% or so, see that it can get at least decent accuracy before we stop and maybe try a stacked CNN. Another question is, are we going to have data augmentation tools to manipulate images to decrease overfitting? That's something we're working on. One of the features we're looking at for next month to start with is some basic data augmentations. So that you can do it inside PerceptiLabs as well, specifically for images. All right, we hit the 90% training accuracy. The validation accuracy has been a little bit lower, but I think we can stop it here and try out some variation to it. I'm hoping to next time show you guys the new test view as well. It would have been in the local version, but unfortunately not on the cloud quite yet. But then we would have been able to inspect the confusion matrix as well to see how many samples were classified correctly from the test data. So let's try. We'll just remove the VGG and we'll instead replace it with 2 convs. Something like that. And let's double the fitch maps here as is fairly standard. And we probably want this to run on ReLU as well. There we go. Alright, so we now have a fairly traditional stacked CNN, although with a little bit less feature maps than usual. I think a very standard one would be 3264. Let's run this one again and see how this one compares. So the biggest difference now is with the VGG we were using before, we would have seen it would have been able to classify a lot quicker than if training from scratch. Since it already had been pre-trained. But that's not always the case, so let's see how this one does. This one is a lot faster, is the first thing we can see. And it's already at 90% accuracy. Cool. So I think the stacked CNN might be the winner for this one. We could try with some dropout as well to make sure the validation accuracy is not as bad. As we can see, the validation loss is going up, which typically means overfitting, which is not something we want. So let's throw in some dropout on this dense layer. Oh wait, is it the convolution layers maybe? Actually, let's do 0.7. We're not working with a massive amount of neurons in this one, since we only have 16 feature maps. And we can do the same for this one. me just run again.